Somewhere on the far side of the solar system, in November of 2018, a signal reached Earth carrying 6 words that a small group of scientists at NASA had been waiting nearly 6 years to hear. Not a discovery of alien life, not a warning of danger, something quieter and, in its own way, more profound. Confirmation that a spacecraft launched during the Ford administration, running on hardware older than the Walkman, had just become the second human-made object in history to leave the solar system entirely. And this time, unlike the first, we were watching it happen in real time, instrument by instrument, as it unfolded. That spacecraft was Voyager 2, and what it recorded at the exact moment it crossed out of our solar system's protective bubble didn't just confirm what scientists already suspected from its twins crossing years earlier. It corrected it, deepened it, and in some places completely rewrote it. This is the story of that crossing, why it mattered so much more than a simple milestone, and why, even now in 2026, scientists are still working through the implications of what Voyager 2 found at the true edge of everything we call home. To understand why this moment carried so much weight, you have to go back to where Voyager 2 started, and to a decision made decades earlier that nearly kept it from ever reaching that boundary with a working set of instruments at all. Voyager 2 launched on August 20th, 1977 from Kennedy Space Center in Florida, 16 days before its twin, Voyager 1, lifted off from the same launch pad. Despite the numbering, Voyager 1 was placed on a faster, more direct trajectory and overtook its sibling within about a year, reaching Jupiter and Saturn first, and eventually leaving the plane of the planets entirely to chase a closer look at Saturn's largest moon, Titan. Voyager 2 took a slower, more patient route, and because of a rare alignment of the outer planets that occurs only once every 175 years or so, mission planners realized they could send it onward past Saturn to Uranus and Neptune as well, an opportunity nobody else would get again for well over a century. Voyager 2 became, and remains to this day, the only spacecraft in history to visit all 4 giant planets up close. It reached Jupiter in 1979, Saturn in 1981, Uranus in January of 1986, and Neptune in August of 1989, discovering new moons and rings at nearly every stop, including the first and still only close-up images humanity has ever captured of Uranus and Neptune. That achievement alone would have secured its place in the history of exploration. But it also meant Voyager 2 spent an extra 9 years traveling through the inner solar system on planetary business, time its twin, freed of any further flyby obligations. After Saturn didn't have to spend. Voyager 1 reached the edge of the solar system first, in 2012. Voyager 2 wouldn't get there until 6 years later, and when it did, it would be carrying something its twin no longer had, a fully functioning plasma science experiment. Here's why that detail matters more than almost anything else in this story. The plasma science experiment is an instrument specifically designed to directly measure the speed, density, and temperature of the solar wind, the constant outward stream of charged particles the sun releases in every direction. Voyager 1's version of that instrument had stopped working all the way back in 1980, shortly after its Saturn flyby, likely due to a failed power component, more than 3 decades before it would ever reach the boundary where that measurement mattered most. So when Voyager 1 crossed the heliopause in August of 2012, the single most direct tool for confirming that crossing, the instrument built to watch the solar wind itself disappear, had already been silent for 32 years. Scientists still confirmed the crossing, but they had to do it indirectly, piecing together a case from a sudden jump in galactic cosmic ray density, subtle shifts recorded by the magnetometer, and other secondary signals that, taken together, painted a convincing but circumstantial picture. It held up under scrutiny, but it wasn't the same as watching the solar wind itself go quiet. Voyager 2's plasma science experiment was still alive, and on November 5th, 2018, it recorded something no instrument had ever measured directly before: the speed of the solar wind around the spacecraft dropping sharply, and then, from that moment forward, reading essentially zero, not inferred from indirect clues, not reconstructed after the fact from a pattern of secondary signals, watched directly as it happened in the data stream itself. "This is what we've all been waiting for," said Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, in NASA's official announcement of the crossing. "Now we're looking forward to what we'll be able to learn from having both probes outside the heliopause." It's worth pausing to actually picture what that data looked like scrolling across a screen at JPL that day. For hours, then days, the plasma instrument had been recording the ordinary familiar signature of solar wind, charged particles streaming outward from the sun at hundreds of miles per second. Exactly the kind of readings the instrument had faithfully recorded for over 40 years. And then, gradually, that signature began to fade, the particle density thinning, the flow slowing, until finally the readings settled into something new and unfamiliar: the colder, sparser, more turbulent signature of the plasma that fills the space between stars. Voyager 2 had crossed the heliopause at a distance of about 11 billion miles from the sun, on the opposite side of the solar system from where its twin had crossed 6 years earlier, becoming the second human-made object to leave the bubble the sun carves out around itself as it moves through the galaxy. That alone would have been a significant milestone. What made it something closer to a genuine scientific turning point was everything that instrument, and the others still functioning alongside it, went on to reveal in the months and years that followed, findings that didn't just confirm Voyager 1's earlier crossing, but actively reshaped how scientists understood the boundary itself. The first surprise involved temperature, and it's the kind of finding that sounds on the surface almost impossible to reconcile with common sense. For decades before either spacecraft reached the heliopause, physicists had modeled the transition zone at the edge of the solar system as a relatively gentle, gradual handoff, the solar wind slowly losing strength, the interstellar medium slowly gaining influence, similar to a river widening and slowing as it nears the sea. What Voyager 2's instruments actually measured at the boundary was nothing like that. Plasma temperatures in the region spiked to somewhere between roughly 30,000 and 50,000 Kelvin, comparable to conditions found near the surface of certain stars, a reading so far outside what models predicted that some science writers began referring to the region informally as a wall of fire. It's a vivid nickname, and it's worth being precise about what it actually means physically, because the honest explanation is, in its own way, even stranger than the dramatic one. There's no combustion happening out there, nothing burning in any conventional sense. Temperature, in physics, measures how fast individual particles are moving, not how much heat they can transfer to something sitting among them. Because the region is so extraordinarily sparse, with particles spread thin across billions of miles of space, there simply aren't enough of them colliding with anything to transfer meaningful heat. Voyager 2 passed directly through a measured plasma temperature that would vaporize almost anything on Earth, and its 40-year-old electronics didn't so much as register a change in operating temperature, because there was almost nothing there to touch it. The second major finding involved magnetism, and it built directly on a puzzle Voyager 1 had first hinted at years earlier, without being able to confirm it. Before either spacecraft reached the heliopause, one of the standard predictions was that the magnetic field environment on either side of the boundary should be dramatically different. Inside the bubble, the sun's own magnetic field, carried outward by the solar wind. Outside, an entirely separate magnetic field generated by the broader structure of the galaxy itself. Two distinct systems from two distinct sources, expected to diverge sharply right at the crossing point. Voyager 1's single magnetometer reading beyond the boundary back in 2012 had suggested something odd. The magnetic field just outside seemed to point in almost the same direction as the field inside. With only one data point, researchers couldn't be sure whether that reflected something real about the boundary itself, or was simply a coincidence, tied to Voyager 1's specific location along an enormous, irregularly shaped edge. Voyager 2 gave them a second, independent measurement taken years later from a completely different position on the opposite side of the solar system. And it showed the same alignment. Two magnetic fields from two entirely different sources, sitting in close agreement with each other at the true edge of everything we call home. NASA's own science communications team described this directly, noting that Voyager 2's observation confirmed what had initially looked like a surprising, possibly coincidental result from its twin. That confirmation turned a curious anomaly into a genuine pattern, one that current theory still hasn't fully explained, and one that suggests our solar system isn't as magnetically sealed off from the rest of the galaxy as earlier models assumed. The third discovery came specifically from where Voyager 2 happened to be positioned when it crossed, a vantage point Voyager 1 never had access to. Voyager 2 crossed closer to the flank of the heliosphere's overall bubble shape, rather than near the leading edge where Voyager 1 had crossed years earlier. From that different angle, one of Voyager 2's particle instruments picked up evidence, described in a statement from the Johns Hopkins Applied Physics Laboratory, that the heliosphere's outer boundary isn't a perfectly sealed barrier at all. A slow trickle of particles from inside our solar system was detected leaking through the boundary into interstellar space, seeping out from the edges even as material from beyond pressed steadily inward. Researchers involved in the analysis described the heliosphere, only half-jokingly, as behaving less like a sealed hull and more like a porous membrane, solid enough to shape and shield everything inside it, but never quite airtight. Then, in early 2024, a new analysis combining years of accumulated data from both Voyager 1 and Voyager 2 suggested something that reshaped the picture even further, and that remains an active area of research today in 2026. Rather than a thin, sharply defined boundary line separating our solar system from interstellar space, the way it's often drawn in simplified diagrams, researchers proposed that the heliopause may actually be a thick transitional layer, a zone where the sun's magnetic field and the galaxy's magnetic field interact and blend gradually rather than meeting at a hard, clean edge. That idea helped resolve a puzzle that had lingered since Voyager 1's original crossing back in 2012, Why the direction of the magnetic field measured by both spacecraft didn't shift the way a genuinely sharp boundary crossing should have produced. Instead of picturing a border like a line drawn on a map, picture something closer to a wide, turbulent coastline where two ocean currents mix gradually across a broad stretch of water rather than meeting abruptly at a single sharp edge. That model remains under active investigation, refined continually as researchers re-examine the archived data from both crossings using newer analytical techniques. This connects to a larger, still unresolved debate that's been running quietly through the field of heliophysics for years, a debate that exists specifically because of the dual perspective Voyager 1 and Voyager 2 together provide. For a long time, researchers generally assumed the heliosphere, our solar system's entire protective bubble, trailed behind the sun's motion through the galaxy the way a comet's tail trails behind its nucleus, stretched long and drawn out in one direction. More recent modeling, built using data from both Voyager spacecraft alongside readings from a separate NASA mission called IBEX, which studies the boundary remotely from Earth orbit by detecting particles that bounce back off it, has suggested the shape might actually be closer to a compact croissant-like curve, deflated rather than stretched into a long tail at all. That disagreement hasn't been fully settled, and every model proposed to explain the heliosphere's true shape has to be built around whatever the two direct data points from the Voyager crossings can support. It's a striking reminder of just how much of our understanding of this entire region still rests on exactly two physical measurements, taken 6 years and billions of miles apart. There's also a puzzle involving distance itself that neither spacecraft's builders could have anticipated. Before Voyager 1 reached the heliopause, scientists expected the boundary's distance from the Sun to shift meaningfully depending on where the Sun happened to be in its roughly 11-year activity cycle, swelling outward during periods of high solar activity and contracting inward during quieter stretches, much like a lung expanding and contracting with breath. Voyager 1 crossed during a period of high solar activity. Voyager 2 crossed 6 years later during a noticeably different point in that same cycle and from an entirely different direction. If the breathing bubble model held up as expected, the two crossings should have happened at meaningfully different distances from the Sun. They didn't. Both spacecraft found the heliopause at almost exactly the same distance, roughly 11 billion miles out, despite crossing at different phases of the solar cycle and from opposite sides of the solar system entirely. "We don't understand why that is," said Stamatios Krimagis, a longtime instrument lead on the mission at the Johns Hopkins Applied Physics Laboratory, in a statement issued alongside the published findings. That's not dramatic language inserted for effect. That's a career physicist, on the record through NASA's own communications office, acknowledging that a basic or reasonable prediction about the shape and behavior of our solar system's edge simply didn't hold up once it was actually tested twice. None of these discoveries happened because engineers planned for them decades in advance. Nobody sitting in a design review in the mid-1970s decided that Voyager 2's plasma instrument should be built to outlast its twins by more than 3 decades specifically to solve a heliopause mystery that didn't even have a name yet. It happened because of ordinary hardware variants, the kind of small manufacturing and operational differences that inevitably separate two nominally identical machines built side by side on the same production line, launched only 16 days apart. And it happened because Voyager 2 simply happened to still be capable of direct measurement at the exact moment it mattered most. Sometimes, the most significant scientific payoff isn't the result of a plan at all. It's the result of one piece of equipment quietly outlasting its twin by exactly long enough to catch something nobody was specifically counting on catching. That kind of accidental redundancy is rare in the history of engineering, and it's a large part of why both spacecraft have continued to be operated with such deliberate, careful attention, even now, nearly 8 years after Voyager 2's crossing, as their power supplies continue fading year after year. Both Voyagers run on radioisotope thermoelectric generators, sealed units that convert the heat produced by decaying plutonium into electricity, and both lose a small, steady, unrecoverable amount of power every single year, with no possibility of refueling or replacement once the source is exhausted. Voyager 2's plasma instrument, the one responsible for nearly all of the findings described here, was finally shut down in October of 2024. Not because it broke, but because the mission team could no longer justify the electricity it required, given everything else on the aging spacecraft that still needed power to keep functioning. It had operated continuously for 47 years, more than 11 times longer than its original design life of 4, and it went dark having already accomplished something no other instrument on either spacecraft ever managed to do. That shutdown, and the broader power crisis both spacecraft are now navigating, has become the central story of the Voyager mission heading into 2026. Voyager 1000's mouse TRs, to where 1 is now the more power-constrained of the two, having already lost 7 of its original 10 instrument packages. Engineers at JPL are currently testing an experimental power recovery procedure, nicknamed internally the Big Bang, designed to restructure how electricity flows through each spacecraft's aging systems and recover small amounts of capacity currently being lost to inefficiency. Because any change to hardware this old carries genuine risk, the team is testing the procedure first on Voyager 2, which currently has a slightly larger remaining power margin, making a failed attempt there less costly to the overall mission. If those tests succeed, the same fix will be attempted on Voyager 1 as well. In a quiet, almost poetic way, the roles between the two spacecraft have reversed from where the mission began. Voyager 2, once regarded as the slower secondary probe on the less glamorous trajectory, trailing behind its more famous twin for most of the mission's history, has become the test bed responsible for helping keep that same twin alive a little longer. Both spacecraft are now expected to lose the last of their usable power sometime in the early 2030s, bringing an end to nearly 6 decades of continuous operation from two machines that were only ever designed to last 5 years. When that silence finally arrives, it won't come suddenly. It will be the last faint signal from an antenna that has been quietly reporting home since before most people alive today were born, arriving after a journey of many hours across a gap so wide that light itself, the fastest thing that exists, takes the better part of a day to cross it. Even after the transmissions stop, neither spacecraft comes to rest. There's nothing out in interstellar space to slow them down, no atmosphere, no meaningful friction, nothing strong enough to meaningfully pull either one off its current course. Both are carrying identical copies of the Golden Record, the gold-plated copper disc holding greetings recorded in 55 human languages, the sounds of rain and ocean waves and human laughter, and 90 minutes of music selected to represent the breadth of human culture across our entire recorded history. The record was assembled by a committee led by the astronomer Carl Sagan, built on the chance that someone, someday, somewhere far from here, finds one of these two aging machines drifting through the dark and wonders where it came from, and who sent it out there in the first place. What Voyager 2 left behind, beyond the record itself, beyond the unmatched close-up views of Uranus and Neptune that only it was ever positioned to provide, is something quieter, but arguably just as significant. Proof that even two nearly identical machines built side by side, launched 16 days apart, can end up telling two very different parts of the same larger story, simply because one of them happened to keep a single, specific instrument alive long enough to directly witness something its twin could only infer from a distance, years earlier, using secondhand evidence. It's a reminder that, in science, the most important discovery isn't always about building something entirely new. Sometimes it's about one aging piece of equipment holding on just long enough to see something for real, instead of everyone having to take someone else's word for it based on circumstantial clues. Nearly 8 years after that signal first reached Earth in November of 2018, scientists are still working through everything Voyager 2's crossing revealed, still refining models of the heliosphere's true shape, still debating exactly why that thick, turbulent boundary layer behaves the way it does, still watching the last two functioning instruments on both spacecraft for whatever comes next, on a fading power supply that gives them less time to find out with every passing year. Whatever Voyager 2 and Voyager 1 still have left to tell us about the true edge of our solar system, they're telling it right now, in real time, with the clock already running on how much longer either one of them will still be able to speak. If you want to see how far that story still goes, this is worth sticking around for. Subscribe if you'd like to follow it.